Ever get that feeling like, the universe is just messing with us?
Yeah, like it's playing some kind of cosmic joke that we haven't quite figured out yet.
Exactly. And today, we're diving into a time when some of the most brilliant minds in history, I'm talking Albert Einstein, suspected just that.
No, this is going to be good. We're talking about the EPR paradox, right?
You got it, the EPR paradox. It's enough to make your head spin, even if you're not a physicist.
And the best part is it's not just some theoretical mumbo-jumbo. This paradox led to real-world experiments.
Okay, so back up for a second. For those of us who haven't quite wrapped our heads around it, what exactly is this EPR paradox?
Yeah, so picture this. It all starts with Einstein and his buddies, Podolsky and Rosen, hence the EPR.
Makes sense.
They were wrestling with this newfangled quantum mechanics, specifically something called entanglement.
Entanglement. That's where two particles are linked no matter how far apart, almost like they're communicating instantly, faster than the speed of light.
You got it. Imagine two tiny spinning particles, and they're linked in this way where they always spin opposite each other. One spins clockwise, the other goes counterclockwise. But here's the kicker. They stay linked, even if they're light years apart.
Okay, see, that's what I'm talking about. That right there feels like the universe messing with us. So were Einstein and his crew saying quantum mechanics was completely wrong?
Not exactly. They felt it was incomplete, like it wasn't telling the whole story.
Okay, so what were they proposing instead?
They thought there had to be some hidden variables, hidden information that we couldn't see yet. Imagine it like this. Imagine those spinning particles. They agreed on their spins beforehand, like before they were separated.
So kind of like, hey, if you spin clockwise, I'll go counterclockwise, that sort of thing.
Exactly. It's like a set of secret instructions they agreed on. They weren't denying the connection, just searching for a simpler explanation, something more in line with how we understand cause and effect.
So they were looking for something a little less spooky, as they called it.
Precisely. Einstein, he always believed the universe, at its core, was elegant, logical.
He just needed to find the missing pieces to prove it. Right. All right, so we've got Einstein and his gang throwing down this EPR paradox, claiming something's missing in our understanding of the universe. But how do we actually test something that's supposed to be hidden? That's where John Bell comes in, right? Bell, he's our guy, huh? He figured out a way to test this whole hidden variable thing.
You got it. Bell came along and said, let's just say, for argument's sake, that these hidden variables are real. If that's the case, what would we see when we run experiments? And you know what? He actually found a way to translate this mind-blowing idea into something we could test in a lab.
Okay, now you've got me really intrigued. How do you go about testing something that's supposed to be hidden? It's like searching for a ghost in a ghost town.
It's a good question, and that's what's so brilliant about Bell's work. He devised a way to look for the fingerprints of these hidden variables, even if we couldn't see them directly. So imagine we've got these entangled particles, right? And we're measuring their spins, but we're looking at them from different angles.
Okay, different angles. I'm with you so far.
Now, here's where things get really interesting. Bell showed that if those particles were pre-programmed with those hidden instructions, the results of our measurements would have to follow specific rules. We call these rules Bell's inequalities.
Bell's inequalities, all right. And these inequalities, they would basically tell us if the particles were following some kind of predetermined plan.
Exactly. If hidden variables were the name of the game, the particle spins would match up more often than not, kind of like they were tipping their hats to those pre-agreed-upon instructions. It would be like finding out those twins actually planned to wear matching socks all along.
So if the experimental results fit within Bell's inequalities, hidden variables win, Einstein breathes a sigh of relief, and the universe makes a little more sense.
You'd think so, right? But the universe likes to keep us on our toes, my friend, because here's where things take a turn for the seriously strange.
Oh boy, hit me with it. What did quantum mechanics predict?
Quantum mechanics, with all its weirdness, actually predicted that Bell's inequalities could be broken.
Broken? You mean those rules they wouldn't always apply?
Not always, no. It was like saying sometimes those twins, even if they tried to match their socks, they'd still somehow end up wearing different ones. Like the act of observing, of measuring the particles, was somehow influencing the outcome.
Wait, hold on. Are we saying that just by looking at these particles, we're changing how they behave?
It's one of the mind-blowing possibilities. And it set the stage for an epic showdown. Einstein's hidden variables, with their predictable universe, versus the wild world of quantum mechanics, where even the act of observation could influence reality.
Talk about a clash of titans. So how did they actually put this to the test? Did we manage to build a sock-detecting contraption for entangled particles?
You're not far off. It took a few decades, but in the 1970s and 80s, some really clever physicists figured out how to entangle photons, particles of light, and guess what they found?
Let me guess, quantum mechanics threw a curveball.
A curveball. It threw a whole new pitch. They found that Bell's inequalities were being violated. The experimental results were even weirder than hidden variables could explain.
So spooky action at a distance, it's real. Like, for real, for real.
It seems that way. It wasn't just some quirk of the theory. It looked like this entanglement thing was a fundamental aspect of how the universe operates.
Wow. So does this mean Einstein was, wrong?
It's not so simple. Remember, Einstein wasn't trying to disprove quantum mechanics completely. He simply felt that something was missing from the picture. He couldn't accept that the universe, at its core, was based on pure randomness, that things could happen without a clear cause, especially across vast distances.
So his intuition wasn't entirely off, he just didn't have all the pieces of the puzzle.
Exactly. And the result of these experiments, confirming the violation of Bell's inequalities, really hammered home just how strange and counterintuitive the universe can be, even for someone as brilliant as Einstein.
This is blowing my mind. We're talking about challenging the very foundation of how we understand the universe. So, where do we go from here? What does it all mean? What are the implications of this whole EPR paradox and Bell's theorem thing?
Okay, my head's spinning a little bit after that deep dive into entangled particles and spooky action at a distance.
It's a lot to wrap your head around.
It really is. So where does this all leave us? What are the implications of this whole EPR paradox and Bell's theorem thing? Like, what's the takeaway here?
Well, it makes you question some of our most basic assumptions about how reality works.
No kidding. It's like we're living in the Matrix or something.
Right. Like, one of the big things it challenges is this idea of locality, the idea that things can only be influenced by their immediate surroundings. Yeah, like how you hitting your computer keys is what makes letters appear on the screen and not something happening on the other side of the world.
Exactly. But Bell's theorem, with all that experimental evidence backing it up, suggests that this idea of locality might just go out the window when we're talking about the quantum world. It's like these entangled particles have some sort of secret back channel, a way of whispering to each other across the universe.
Okay, that is seriously strange.
It is. And there's this concept of realism in physics, the idea that properties exist in a fixed objective state, whether or not we measure them.
Okay, can you give me an example?
Sure, like the color of a ball. We assume it's red whether we look at it or not, right?
Right.
But the violation of Bell's inequalities suggests that at the quantum level, things might not be so clear-cut, so definite.
So you're saying that at the quantum level, things might not even have a definite state until we observe them. What, like the moon isn't really there when we're not looking at it?
Well, it's not quite that drastic, but it does suggest that our active observation might play a more fundamental role in shaping reality than we previously thought.
This is blowing my mind.
I know, right? It's a lot to process. But think about the implications.
Okay, I am trying. What are some concrete examples?
Well, for one, understanding these strange quantum phenomena has already led to some pretty incredible technological advances.
Really? Like what? Give me an example.
Take quantum cryptography, for instance. It uses the principles of entanglement to create ultra-secure communication channels. Imagine a world where it's impossible to eavesdrop on a conversation.
Whoa, that would change everything.
Exactly. It's all thanks to this spooky action at a distance that seemed so bizarre at first.
So this isn't just some theoretical physics locked away in a lab. It has real-world applications.
Oh, absolutely. And then there's quantum computing, which has the potential to revolutionize everything from medicine to material science.
Okay, so we're talking potentially groundbreaking changes in the future because of this spooky action.
We are. And, beyond the practical applications, I think there's something really profound about grappling with these concepts. The EPR paradox and Bell's theorem, they really force us to expand our understanding of the universe and our place in it.
It really is humbling when you think about it, isn't it?
Totally. It reminds us that there are still mysteries out there, wonders we're only just beginning to explore, and that maybe, just maybe, the universe is even stranger and more marvelous than we ever imagined.
And that's what I love about these deep dives. They always leave me with more questions than answers.
Me too. It's a good reminder to stay curious, right?
Absolutely. Well, that's all the time we have for today's deep dive. A big thank you to our expert for joining us and for illuminating this mind-bending topic.
My pleasure. It's always a blast talking about this stuff.
And to our listeners, a huge thank you for tuning in. Next time you look up at the stars, remember those tiny points of light might be connected in ways we're only just starting to grasp, thanks to the legacy of Einstein, Podolsky, Rosen, and of course, John Bell.
It's a wild, entangled universe out there.
It sure is. Until next time, keep those minds curious.
Buckle up, everyone, because today we're going deep into the quantum realm. Yeah, that mysterious place where, well, things get seriously weird. We're talking about one of the biggest head-scratchers in physics, something that even the amazing Albert Einstein couldn't quite wrap his head around.
Yeah, you said it. The quantum world can really make you wonder. It all started with this thought experiment, right? A seemingly simple question that turned out to have really, really deep implications. Can quantum mechanics really be the full story? Or is there something deeper, something hidden, governing everything in the universe?
So that's where our deep dive begins.
Exactly, right here. With this groundbreaking paper published in 1964 by physicist J.S. Bell, this wasn't just any paper. It was like a bolt from the blue, totally shaking up physics as we knew it.
It's a pretty intense paper. What did it reveal?
It revealed a universe even stranger, even weirder than anyone had dared to imagine.
I'm ready for this. Lay it on me.
Well, it all revolves around this thing called the Einstein-Podolsky-Rosen paradox.
Okay. Catchy name. But come on, what is it really about?
You know, physicists, we like to keep things simple. So, EPR for short.
EPR, got it. So what does EPR throw light on?
Well, it throws a spotlight on one of the weirdest, most mind-boggling aspects of quantum mechanics. Entanglement.
Okay, entanglement. Sounds intriguing. What's that all about?
Okay, so imagine this. Two particles linked together in a way that even when they're separated by, like, vast distances.
Yeah, like across the universe from each other.
Yeah, exactly. Measuring one of them seems to instantly affect the other one, no matter how far apart they are.
Whoa, hold on. That sounds like something straight out of Star Wars. Are we talking faster than light communication here?
That's what it looks like. Picture this. You flip two coins at the same time, right? With these entangled particles, if one coin lands on heads, boom, the other one, even light years away, will automatically land on tails. Every single time. It's like they're secretly talking to each other faster than the speed of light.
Okay, that's just plain spooky. No wonder they call it a paradox.
You got it. Spooky! It's like those particles have some kind of ESP or something. And you know what? This spooky action at a distance, as Einstein famously called it, it really bugged him.
Really? It bugged him. Why? I mean, it is pretty wild.
It just didn't fit with his whole understanding of how the universe should work, right? It looked like the universe was breaking his rules, and Einstein, well, he didn't like that one bit.
So he wasn't a fan of spooky action at a distance. What did he think was really going on then?
Well, Einstein, he was all about a universe that was elegant, predictable. He believed that quantum mechanics, as weird as it seemed, couldn't be the whole story, couldn't be the final word. He figured there had to be a simpler explanation.
Simpler than two particles talking to each other across the universe. Okay, I'm listening. What did he propose?
He argued that there had to be something we were missing, something hidden from view. He called them hidden variables, like secret ingredients in the recipe of reality that would make everything nice and predictable again.
Okay, so these hidden variables, they were like Einstein's way of saying, hold on, there's got to be a more logical explanation for all this quantum weirdness.
Exactly. He believed that these hidden variables, once we discovered them, would reveal a universe that still played by the rules, a universe that was still, at its core, predictable. No more spooky action, no more instantaneous communication, just cause and effect.
So it's like Einstein was saying, don't get too freaked out by entanglement, everyone. There's a perfectly reasonable explanation for it. We just need to find it.
Yeah, and that's where our friend John Bell enters the scene.
Ah, J.S. Bell. The physicist who shook things up with his 1964 paper.
The one and only. Bell, he was like, okay, Einstein, I hear you. You have this hidden variable theory, this idea that there's more to the story than meets the eye. Let's put it to the test.
Oh, I like where this is going. So Bell set out to prove Einstein right.
Well, he wasn't necessarily trying to prove Einstein right or wrong. Bell, he was a true scientist. He just wanted to know the truth, whatever it might be. So he came up with this ingenious mathematical tool, this incredibly clever test, and we call it Bell's inequality.
Bell's inequality, huh? Sounds intense. What does it do?
It's actually kind of elegant when you get down to it. Bell basically said, all right, if hidden variables are the answer, if they're really pulling the strings behind the scenes, then the results of certain experiments should follow specific patterns. They'll have to obey certain limitations, or, to use the technical term, they have to stay within these boundaries.
Okay, so Bell created this mathematical obstacle course for the hidden variables to navigate.
Exactly. It was a test, a challenge. He was saying, if you're real hidden variables, then you have to be able to jump through these hoops.
So what happened? Did the hidden variables pass the test?
Well, that's where things get really interesting, because when physicists actually started doing these experiments, measuring the properties of those entangled particles, something amazing happened.
Don't keep me in suspense. What happened?
The results, they were totally unexpected. The results straight up defied Bell's inequality.
Wait, what does that mean?
It means those hidden variables. They tripped on the obstacle course. They couldn't quite stick the landing. It was as if the universe itself was saying, nope, Einstein, that's not how I roll.
So Einstein's hidden variables were a bust. What does that mean for our understanding of the universe?
It means, my friend, that the universe might be even weirder, even more mind-boggling than even Einstein could have imagined.
You got to be kidding me. Weirder than entangled particles. We've got to dive deeper into this. But first, a quick break. Okay, so we're back and my head is still spinning from that bombshell. Quantum mechanics, no hidden variables, and a universe weirder than Einstein thought possible. Where do we even go from here?
It's a wild ride, that's for sure. But this is where things get really interesting.
Okay, I'm listening. What could be more interesting than entangled particles and spooky action?
Well, Bell's theorem, it doesn't just tell us what's wrong with the hidden variable theory.
What does it do then?
It gives us a glimpse, a peek behind the curtain at how the universe might actually work.
Okay, now you've got my attention. Break it down for me. How does it do that?
The most mind-blowing implication of Bell's theorem is that the universe, well, it might just be inherently non-local.
Non-local. Now, there's a term I haven't heard before. What does that even mean?
Okay, so imagine you have this idea, right, that things can only be influenced by, like, their immediate surroundings. Like, you hit a billiard ball, it moves because of the force from the cue stick, right? Cause and effect happening right there in front of you.
Yeah, that makes sense. Stuff doesn't just move on its own.
Exactly. That's locality, things interacting directly with their neighbors. But Bell's theorem, it throws a wrench into that neat and tidy picture.
Oh, no. So you're telling me that things can just randomly be influenced by things super far away?
Not randomly exactly, but in the quantum realm, things aren't so clear-cut. It's like those entangled particles, even when they're light years apart, they're still part of this single unified system. They're connected in a way that goes beyond our everyday experience of space and time.
So you're saying that something I do here, like right now, could instantly have an impact on something way out there in the Andromeda galaxy. It's like the universe has some sort of cosmic telepathy going on.
It's a mind-blowing idea. But hold your horses, it's not quite as simple as that. Bell's theorem, it doesn't mean we can send messages faster than light, like some kind of cosmic text, or that we can control events across the universe.
Okay, so no quantum texting just yet. But I mean, this still has to be huge E for how we see the universe, right?
Absolutely. Bell's theorem, it throws a real curveball at our classical view of reality, that whole idea of a clockwork universe where everything is separate and independent. It suggests that at the most fundamental level, the universe might be far more interconnected, far stranger than we ever imagined.
This is blowing my mind. So how did other physicists react when Bell dropped this bombshell? I mean, talk about a paradigm shift.
You said it. You can imagine the reaction. I mean, some physicists, they clung to that hope that there was some loophole in Bell's theorem, some way to salvage that classical picture of the universe.
And what about the others?
Others, they saw it as this incredible opportunity, this open door to a whole new frontier of physics. They dove headfirst into exploring the strange and wonderful world that Bell had revealed.
A new frontier of physics, huh? So what are some of the rooms in this new frontier? What's got physicists so excited?
Well, one of the most exciting rooms, without a doubt, is the room labeled quantum computing.
Quantum computers, I've heard of those. They use the power of entanglement to perform calculations, right? Calculations that regular computers could only dream of.
You got it. We're talking about mind-boggling processing power, like cracking codes that would take classical computers billions of years in the blink of an eye.
That's incredible. And to think that it all stems from this mind-bending concept of entanglement.
That's the beauty of it all. Bell's work, it's not just some abstract theoretical idea anymore. It's paving the way for technologies that could completely revolutionize our world.
Okay, I have to ask, what about the philosophical side of things? This has to have some pretty wild implications for how we see ourselves, right?
Absolutely. One of the things Bell's theorem forces us to reconsider is this: the role of the observer in shaping reality.
Okay, hold on, we're getting deep now. The role of the observer. You mean like how we perceive the world actually changes it?
It's a heady concept. In classical physics, the observer is separate. We observe, we measure, but our presence doesn't fundamentally change the thing we're observing, right? But in the quantum realm, things are fuzzy. The very act of observing, of measuring a quantum system, seems to play a role in determining what we actually observe.
So you mean like our very act of looking at the universe forces it to choose one possibility over another, like we're collapsing the wave function just by observing it?
Exactly. It's like the universe is saying, hey, I'm not going to show you all my cards at once. You get to choose which aspect of reality you want to see.
That is both amazing and terrifying at the same time. It's like we're not just passive observers in the universe, we're active participants in shaping it, even if we don't fully understand how.
And that right there, that's the beauty and the mystery of Bell's theorem. It's not just a physics problem, it's a doorway to a whole new way of understanding the universe and our place within it.
So much to think about. Bell's theorem, entanglement, the role of the observer. It's like the universe is playing a giant game of cosmic hide and seek. The more we uncover, the more questions we seem to have.
I think that's a great way to put it. We keep trying to pin down reality, to define it, to put it in a box, and the universe just keeps finding new ways to surprise us. Bell's theorem really throws a wrench in the works.
It definitely does. So as we start to wrap up our deep dive into Bell's theorem, what's one of those lingering questions that you find particularly fascinating? What's got you staring out the window at night, wondering?
Well, it's a question that's been debated for centuries, but Bell's theorem really throws a whole new light on it.
Okay, you've got to tell me what's the question.
The question is this: is the universe fundamentally deterministic? Or is there something else? Is there an inherent randomness at play?
Okay, determinism versus randomness. Those are some big ideas. So determinism, that's the idea that everything in the universe is predetermined, right? Like a giant clockwork mechanism set in motion at the beginning of time.
Exactly. Every event, every decision, every thought, all predetermined from the moment of the Big Bang.
And randomness, that's the opposite. That there's some element of chance, of unpredictability that influences how things unfold.
Yes.
Yeah.
That at the most fundamental level, the universe is governed by probabilities, not certainties. And that even if we knew everything there is to know about the present, we still couldn't predict the future with absolute certainty.
So which is it then? Are we just cogs in a giant cosmic machine, or are we part of a grand, unpredictable dance?
That's the million-dollar question. Bell's theorem, it doesn't tell us which is right, but it does strongly suggest that there's more to the story than just a simple deterministic universe. This inherent uncertainty, this randomness at the quantum level, might be essential for the universe as we know it.
It's almost a beautiful thought that something as seemingly chaotic as randomness could be the source of such incredible complexity and beauty.
Isn't it? It's like the universe is saying, hey, I'm not just a predictable machine. I'm a work in progress, constantly evolving, constantly surprising myself. And who knows, maybe this randomness, this unpredictability is what allows for things like free will, creativity, even consciousness itself.
It's a humbling thought and a little bit awe-inspiring to think that our universe might be governed by both order and chaos. That even with all our scientific advances, we're still just scratching the surface of understanding the true nature of reality. Well, a huge thank you to J.S. Bell for giving us so much to ponder, and to all of you for joining us on this incredible journey into the quantum realm. Until next time, keep exploring the universe and keep asking those big questions. And never forget, sometimes the most profound discoveries are the ones that leave us with even more questions than answers. All right, so today we're diving into some seriously mind-bending stuff. We're talking about a clash of titans, Einstein versus quantum mechanics. It's a thought experiment that kind of threw a wrench into how we understand reality, you know?
Yeah, it's pretty wild. It all started with Einstein basically challenging a theory he helped create.
He wasn't exactly on board with all the quantum weirdness, huh?
Not really, no.
So to get into it, we're looking at the work of J.S. Bell, specifically his paper on the Einstein-Podolsky-Rosen paradox, or the EPR paradox for short.
Right, the EPR paradox. Basically, Einstein and his colleagues, they were trying to show that While quantum mechanics could make these crazy accurate predictions, it had to be missing something fundamental. They thought there had to be these hidden variables at
Yeah.
play, something extra, you know?
Hidden variables, like secret ingredients the theory was missing. Okay, I kind of like that.
Yeah, that's
So,
it.
like, we can predict the weather patterns and all that, but there's got to be something more that decides whether it rains on your picnic, right?
Yeah,
Something we just can't quite measure.
that's a good way to put it. But the EPR paradox actually goes a step further than that. Imagine two particles, and they're linked in this special way where if you measure one, boom, you instantly know something about the other one, even if they're light years apart.
Hold up. That's like I put on a glove here, and somehow, instantly, I know if the other glove is left or right-handed, even if it's like on Mars or something.
Just sound crazy.
Yeah, that sounds less like physics and more like, I don't know, magic or something.
That's what Einstein thought, too. This idea, this spooky action at a distance, it really bothered him. He felt like it violated this fundamental rule in physics we call locality. It's this idea that things can only be directly influenced by their immediate surroundings.
Right, so no long distance calls for particles.
Gotcha.
Exactly. And that's where J.S. Kill comes in, right?
Right.
And he doesn't just argue about it. He's like, all right, let's put this to the test. He actually creates a mathematical proof.
Exactly. And his work, it didn't just challenge the EPR paradox. It set the stage for some incredible experiments that really pushed the boundaries of what we thought we knew. See, at the heart of his paper is this idea of local realism.
Okay, local realism.
Yeah, so we've talked about locality, that things can only be directly influenced by their immediate surroundings. Well, realism in this sense means that when we measure something, we're just revealing a property that already existed. We're not creating it by observing it, you see.
So no observer effect shenanigans going on. The universe isn't just making things up as it goes along.
That's the question, isn't it?
Yeah.
And Bell's theorem, well, it kind of throws a wrench in that idea. It demonstrates that if we cling to this concept of local realism, we can't fully explain the predictions that quantum mechanics is making.
So it's like the universe is giving us this ultimatum, right? Choose your fighter, classical physics or quantum weirdness. You can't have both.
It's like, you know those puzzles where you got to fit the right shape through the hole? Local realism, it's like we're trying to jam a star through a square hole when it comes to quantum mechanics. Something's got to give.
So how do you actually prove this? Did he have like a special cosmic calculator or something?
Well, he used math, that's for sure. But it's more like elegant math. Imagine this. Okay, you got these two particles, entangled, could be miles apart, light years even, doesn't matter. And you've got these measuring devices, one for each particle.
Okay, I'm picturing it. Giant cosmic science experiment, lasers, maybe some dry ice for dramatic effect.
Exactly. So Bell, he's thinking, all right, if these particles are just carrying some hidden instructions, if they're playing by the rules of local realism, what kind of results should we see when we take these measurements? And the answer,
Well, it really threw everyone for a loop.
the universe was like, nope, not that simple, pretty much. You see, if local realism was the name of the game, if finding a right-handed glove here meant nothing about the left-handed glove light years away, then the measurements, they should be random, right? Like a coin toss.
Makes sense to me.
But quantum mechanics and Bell's math, they were saying something totally different. They said those measurements, those correlations would be way stronger, way more connected than a simple coin toss.
So it's like the universe is playing poker, but with loaded dice. And the experiments, they back this up.
Oh, yeah. Tons of experiments, and they all basically confirmed it. The quantum world, it just doesn't play by our usual rule. It's like the rule book got thrown out the window, and we're just starting to pick up the pieces.
All right, but here's the real kicker. Bell's theorem, it doesn't say which principle's the problem.
Yeah.
It's like, what are your fundamental assumptions about reality? Yeah, it's wrong. Good luck figuring out which one.
Exactly. And that's the real mind bender.
So are we saying that things can be influenced by things super far away, or that things aren't really real until we look at them? Or both?
Those are the million-dollar questions. Bell's work, it didn't give us all the answers, but it gave us the questions. And more importantly, it showed us how to start testing for those answers.
So less philosophy, more, let's roll up our sleeves and do some cosmic detective work.
Now you're getting it, because the implications of this, they are huge. I mean, just think. If we can instantly influence something light years away, what does that mean for the speed of information?
Faster than light communication, huh? That's straight out of Star Trek. Sign me up.
It's easy to get carried away, right?
Mm-hmm.
But Bell's theorem, it's more like it opens up these big questions. It doesn't necessarily give us all the answers, at least not yet.
Okay, so no warp drive just yet. But what about that other possibility? that things aren't really real until we look at them. That's just, I don't even know. Does that mean the moon disappears when we're not looking?
Well, it's not quite that simple, but you've hit on a really big mystery in quantum mechanics. The measurement problem.
The measurement problem.
Yeah, it's something that's been bugging physicists for decades now.
So it all goes back to those hidden variables, Einstein's big idea.
Yeah.
So if realism is the problem, maybe, like the properties of things, they aren't really set until we measure them. It's like the universe is playing hide and seek with reality itself.
Exactly. And you know what's even more interesting? Bell himself, even when he was presenting these potentially groundbreaking ideas, he was really cautious.
Really? The guy who basically said, Einstein, you might be wrong about reality, was being cautious. Tell me more.
Well, if you go back and actually read his paper, it's amazing how carefully he words things. He never actually comes right out and says, Einstein, you were wrong. Instead, it's more like, look, if we want to hold on to both quantum mechanics and our classical understanding, then something has to give, you know?
So it's more like, hey, the math adds up, the experiments seem to agree, but maybe I'm missing something. That's really something, especially when you think about how much his work kind of changed everything.
It is. And honestly, for me, that's what makes this whole topic so fascinating. It's not just about the particles and equations, you know. It's about how we understand the universe, about wrapping our heads around a universe that constantly surprises us.
It really makes you want to just look up at the stars and wonder what's really going on out there.
Exactly. That sense of wonder, that's what we were hoping to spark with this deep dive. The implications of Bell's theorem, the mysteries it revealed about what's real, about how things can influence each other, it's all still unfolding.
These aren't just like abstract ideas either. It's driving some of the most cutting-edge physics research happening right now.
Absolutely. And who knows what we'll discover next? That's the beauty of it.
So if you're looking for a good mental workout, something that might just break your brain a little, but also open it up to a whole universe of possibilities, well, you've come to the right place. This deep dive, it was just the beginning. We encourage you to keep digging, keep questioning, keep exploring. Who knows, maybe you'll be the one to unlock the next big secret of the quantum world. You think you know weird? Okay, get ready, because today we're diving into a paper that really shook up the foundation of quantum mechanics.
Ooh, sounds intense.
It is. We're talking about a 1964 paper by physicist John S. Bell called, get this, on the Einstein-Podolsky-Rosen paradox.
The EPR paradox. Now, that's a classic.
Absolutely. And, you know, our listeners are all pros when it comes to quantum entanglement, so we'll skip the 101.
Right, straight to the good stuff.
Exactly. But for context, this paper digs into that thought experiment, the EPR paradox. Imagine like two particles. They've been chilling together since the Big Bang.
Okay, I'm picturing it.
Now, they've gone their separate ways, and we're
Yeah.
talking like opposite ends of the universe far. But here's the thing. Quantum mechanics, that rebel of the physics world, suggests that if you measure one particle, it instantly messes with the other one, no matter how far apart they are.
The ultimate long-distance relationship.
Right. Like, are they cosmically texting each other? Einstein was not a fan.
Yeah, spooky action at a distance wasn't exactly his cup of tea. What's so interesting is that Einstein, along with Podolsky and Rosen, they thought this spooky action thing meant something big was missing from quantum mechanics.
Like a glitch in the Matrix.
Kind of. They figured there had to be these hidden variables. Think of them like secret instructions the particles got way back when. These instructions, they argued, would explain how the particles were connected without needing to communicate across the universe instantly.
So I can almost hear Einstein saying, hold on a minute, there's got to be a more logical explanation.
Exactly. And that's where John Bell steps in with his theorem, ready to put these hidden variables to the test. He basically asked, could these hidden variables really explain things without any spooky action? And get this, he found a way to test it, not in a lab, but with math.
Whoa, a theoretical physics showdown.
You got it. In one corner, spooky action at a distance, and in the other, these mysterious hidden variables. And Bell's weapon of choice, the concept of locality. It's a simple idea. What happens in one place can only be directly affected by things happening right there, right now.
Makes sense.
Right. Even in the bizarre world of quantum mechanics, this idea of locality just seems right. And you know, Einstein was all about it.
Oh, I bet. He was all about clear, elegant explanations. Didn't he famously say something like, we should totally stick to the idea that messing with something over here shouldn't instantly mess with something way over there?
He did. But how do you test something as mind-bending as spooky action? You turn to the language of math.
And that's precisely what Bell did. Okay, so Bell, he comes up with this thing called Bell's inequality.
Catchy name.
Right. And I know inequality, it sounds like something straight out of high school math class. But stay with me here.
Okay, I'm listening.
Imagine like you have two dice, but they're rigged, right? So they always land on the same number. No matter how far apart you roll them, if you get a 3 on one, bam, the other one's a 3 too.
Okay, I'm with you.
So Bell's inequality, it's kind of similar, but instead of dice, we're talking about the properties of our entangled particles. Bell said if those hidden variables were really controlling things, and this idea of locality held up, then the correlations between our particles, they'd have some boundaries. Like there'd be a limit on how often they could match.
It's like you're setting a speed limit on how in sync those dice rolls can be. If they were truly random, there's only so much they could match up, right? Bell found a way to take that same logic and apply it to the quantum world.
So it became this ultimate test.
Yeah.
Would reality play by Bell's rules, meaning hidden variables were calling the shots, or would something totally wild happen?
And here's where it gets really cool. Physicists, they could actually test this Bell's inequality in a lab. They set up these experiments with entangled particles, measured their properties, and then crunched the numbers.
Putting that theory through the ringer. So, drum roll, please. What was the verdict? Did Einstein and his hidden variables have it right? Or did quantum mechanics have another trick up its sleeve? Well, the results are in.
And let me tell you, they really shook things up.
I bet. So, spill the quantum tea.
The experiments, they showed that those correlations between the entangled particles, they could actually go past the limits that Bell's inequality set.
Whoa. So it wasn't just some like theoretical thing.
Correct.
Spooky action at a distance was real.
Real and breaking the rules, at least the rules we thought we knew.
Defying all our logical, everyday world expectations.
Right. It's like the universe is playing a giant game of cosmic tag, but nobody told us the rules, you know?
Mind-blowing. But what I find even more wild is that
What's that?
Bell's paper, it didn't just like stop at proving Einstein wrong.
Yeah, it went there.
It dove into the so what of it all.
Exactly. It opened up this Pandora's box of questions. Like, what does this non-locality thing really mean, you know? Does it completely shatter our whole understanding of cause and effect?
Right.
Like, could there be some other thing going on, some deeper principle we haven't even thought of?
It's like we went looking for Atlantis and stumbled upon a whole new continent.
That's a great way to put it. And you know, Bell, he even threw out this one really interesting idea.
Oh yeah, what was that?
He said, what if, now just hear me out.
I'm all ears.
What if quantum mechanics, the way we understand it now, only works when you've already decided how you're going to set up the experiment?
Interesting.
Could there be some kind of faster-than-light communication happening behind the scenes?
Like the universe is sending a memo?
Exactly. Like, hey, this is how we're playing this time. It's as if Bell was saying, look, we just threw out one big assumption. Who's to say there aren't others?
So cool.
It is.
This deep dive, it wasn't about right and wrong answers.
It was about, like, pushing the boundaries of what we thought we knew.
Exactly. It really makes you think,
Definitely. There's still so much to explore.
Well, there you have it, folks.
A single paper that turned the physics world upside down.
It's enough to make your head spin, but in the best way possible.
Totally agree. It's these kinds of mysteries that keep me excited about physics.
Me too.
Yeah.
And if you're out there, dear listener, and this conversation has got those neurons firing, we want to hear from you. Head over to our website, leave a comment, tell us what you think. And until next time, keep those minds curious.
Okay, get ready, because we're about to dive into some seriously mind-bending territory today. We're talking about a concept that shook even Einstein to his core. Imagine this. Two particles, linked in a way that seems to defy the very laws of physics. You change one, and the other changes instantly, no matter how far apart they are. We're talking across galaxies, even. It sounds like something straight out of Star Trek, but this is the essence of the EPR paradox.
Yeah, it's a puzzle that has baffled physicists for almost a century. And it all boils down to this deeply unsettling idea of spooky action at a distance.
Right, and today we're going to untangle this mind-boggling paradox by taking a deep dive into a paper by J.S. Bell, published back in 1964. It's called On the Einstein-Podolsky-Rosen Paradox, and it really throws a wrench into our classical understanding of how the universe works.
It really does. You see, the EPR paradox gets its name from the physicists who first stumbled upon this quantum enigma, Einstein, Podolsky, and Rosen. Back in 1935, they published a paper questioning whether quantum mechanics, as we understood it, was truly complete. They proposed this thought experiment, which we now call the EPR paradox, to highlight what they saw as some serious shortcomings in the theory.
So they were basically saying, hold on, something's missing from this quantum picture.
Exactly. They felt that quantum mechanics, while incredibly successful in predicting experimental results, couldn't possibly be the whole story. It was like describing a car perfectly without acknowledging the existence of an engine.
So they were looking for the quantum engine, so to speak.
Precisely.
Right.
Einstein, in particular, was deeply troubled by what he called spooky action at a distance, which is this idea that two particles could be linked in such a way that measuring one would instantly affect the other, even if they were light years apart.
Right, because that would mean somehow information was traveling faster than the speed of light, which, according to Einstein's own theory of relativity, was impossible.
Exactly. It violated everything we thought we knew about locality, the idea that things can only be influenced by their immediate surroundings.
So how do you even begin to wrap your head around this? Where do we even start?
Well, Bell starts with a thought experiment. Imagine two particles linked in what we call a singlet state. Now, for the sake of simplicity, let's picture these particles as two coins. But here's the catch. These coins are linked in such a way that if one lands on heads, the other one must land on tails.
Okay, so it's like they're two sides of the same coin, even when they're separated.
Exactly. Now imagine these linked particles flying away from each other at incredibly high speeds, potentially even across the vast expanse of space. And here's where it gets really weird. If you measure the spin of one particle and find it spinning, say, clockwise, you instantly know that the other particle, no matter how far away it is, must be spinning counterclockwise.
It's like they have some sort of secret communication channel that operates outside the normal bounds of space and time. But Einstein just couldn't accept that something could travel faster than light?
Right. He thought there had to be a more rational explanation. And that's where the idea of hidden variables comes in. He proposed that maybe, just maybe, there were some hidden factors, some unknown properties within these particles that were predetermining their behavior from the very beginning.
So it's like each particle has a tiny instruction manual hidden inside telling it how to behave during a measurement.
Exactly. And this instruction manual, that's your hidden variable. If this were true, then the particles wouldn't know to be communicating instantly. They would just be following a predetermined plan.
Okay, so that would explain away the spookiness, right? But how do you actually test for something that's supposed to be hidden? That seems like trying to find a black cat in a dark room, right?
Well, that's where Bell's brilliance really shines through. He found a way.
So how did he do it? How do you test for something you can't directly observe?
Well, Bell was a mathematician at heart, and he found a way to translate this mind-boggling physics problem into the language of mathematics. He came up with what we now call Bell's inequality.
Okay, and what exactly is an inequality in this context?
In simple terms, it's like a boundary line. Bell's inequality says that if these hidden variables, these predetermined instructions, were really the explanation for the behavior of these entangled particles, then the results of certain experiments would have to fall within a specific range, within this boundary.
So it's like saying, if the universe works this way, with hidden variables and all, then we should see these experimental results clustered within these limits.
Exactly. But here's where it gets really mind-blowing. Bell showed that according to quantum mechanics, the actual experimental results should fall outside of this boundary.
So it's like quantum mechanics is saying, nope, not going to play by your hidden variable rules.
Precisely. Quantum mechanics, in a sense, breaks Bell's inequality.
That's incredible. So this inequality wasn't just some theoretical idea, right? We could actually test it in a lab.
Absolutely. And that's exactly what physicists started doing in the decades after Bell published his paper. They devised incredibly clever experiments to test these predictions.
What did they find?
Well, the results were stunning. Time and time again, these experiments, while incredibly complex and sensitive, showed that quantum mechanics was right. The experimental results consistently fell outside of the bounds set by Bell's inequality, essentially ruling out most of the plausible hidden variable theories.
So it's like the universe itself was saying, hidden variables. Nope, not how I roll.
You could say that. It was a major victory for quantum mechanics and a profound realization that the universe is far stranger than we could have ever imagined.
So we're really saying that this spooky action at a distance, this seemingly instantaneous connection between particles is real. There's no other way to explain the experimental
That's
results.
the mainstream interpretation, yes. And it sent shockwaves through the world of physics.
It's like our intuition about how reality should work just completely breaks down at the quantum level.
It really does. It challenges everything we thought we knew about locality, causality, and the very nature of reality itself.
So where do we even go from here? What are some of the big unanswered questions that scientists are still grappling with in light of Bell's theorem?
Well, one of the biggest questions is how. How does this spooky action actually work?
Yeah, if there's no hidden information traveling between these particles, how are they communicating?
That's the million-dollar question, and unfortunately, we don't have a definitive answer yet. There are many interpretations of quantum mechanics, each offering a different perspective on what might be going on. But one thing's for sure, Bell's theorem didn't just expose a mystery. It gave us a tool, a way to test the very foundations of reality.
It's like we've stumbled upon this incredible new continent of knowledge, like you said, and we're just beginning to explore its potential.
And that's what makes this so much more than just some abstract physics debate. It really could change everything.
Okay, so walk me through this. How could something this bizarre, this fundamentally counterintuitive, actually affect our lives?
Well, for one, it's pushing the boundaries of quantum computing. We're talking about harnessing these very principles of entanglement and superposition to perform calculations in ways that classic computers could only dream of.
So the same spookiness that puzzled Einstein could one day lead to these mind-blowing breakthroughs we can't even imagine.
It's not just about faster computers, though. It's about tackling problems that were once thought to be impossible. Drug discovery, material science, cryptography, artificial intelligence, all of these fields could be revolutionized.
It's almost as if we've stepped into a science fiction novel, but it's actually happening right here, right now.
It goes even deeper than that, though. Think about causality, the idea of cause and effect. If these particles can be linked across vast distances, influencing each other instantaneously, does that mean our traditional understanding of cause and effect needs a rethink?
Wow, that's a pretty profound question. It's like Bell's theorem has opened up a Pandora's box of possibilities, but also a Pandora's box of really big questions about how the universe actually works.
And that's the beauty of science. Every answer seems to bring about more questions, pushing us further and further down the rabbit hole of knowledge.
So what's next? What are the big mysteries that scientists are wrestling with right now, thanks to Bell's theorem?
One of the biggest mysteries is understanding exactly how this spooky action at a distance actually happens. What are the mechanisms at play? Is there some sort of information being transmitted between these particles? And if so, what does that tell us about the nature of information itself?
Right, because we've always thought of information as something that needs a medium to travel through, but this seems to defy that.
Exactly. It challenges our fundamental assumptions about how the universe operates.
So while we might not be beaming ourselves across the galaxy Star Trek style anytime soon, we're definitely venturing into uncharted territory. And it's all thanks to this mind-blowing concept that Einstein himself struggled to accept.
It just goes to show that the universe is far stranger and more wondrous than we could have ever imagined.
This deep dive has been a wild ride, and it seems like we're just getting started. Big thanks to you for breaking down these incredibly complex concepts in a way that we can all grasp.
It's been my pleasure. I always enjoy diving into these fascinating topics.
And to our listeners, we hope this deep dive has left you with a sense of wonder and maybe even a few more questions of your own. After all, that's what this is all about, embracing the unknown and venturing into the great beyond of knowledge. Until next time, keep exploring and keep those minds open. So last time we were talking about how Bell's theorem really throws a wrench into our classical understanding of cause and effect.
Right, because if these particles can be linked across vast distances, if they can influence each other instantaneously, it really makes you question our everyday notions of cause and effect.
Yeah, it's like the universe is playing by a whole different set of rules down at the quantum level.
Exactly, and that's what makes this so exciting.
Okay, so let's say we accept that this spooky action at a distance is real. What's next? What are the big questions, the big mysteries that scientists are trying to unravel now?
Well, one of the biggest mysteries, and it's a question that has haunted physicists for decades, is how? How does this spooky action actually work?
Yeah, if these particles aren't sending secret messages faster than light, if there's no hidden information being transmitted, how are they connected in this way?
It's like they have this invisible thread connecting them, even across the vastness of space, and if you tug on one end of the thread, the other end feels it instantly.
It's mind-boggling, really. But it seems like this spookiness, as unsettling as it is, could actually hold the key to some incredible breakthroughs.
Absolutely. Think about quantum computing, for example. We're talking about harnessing the power of entanglement, this very spooky action, to perform calculations in ways that would make even the most powerful supercomputers look like toys.
It's like we've stumbled onto a whole new set of tools, a whole new way of thinking about computation.
It's not just about speed, though. It's about tackling problems that were once considered impossible. Imagine developing life-saving drugs, designing completely new materials, creating unbreakable encryption. These are just a few of the potential applications of quantum computing.
It's like we're on the cusp of a technological revolution, and it's all thanks to this spooky action at a distance.
And the implications go even beyond technology. Bell's theorem has really forced us to rethink our fundamental understanding of reality. It's challenged our notions of locality, causality, and even what it means for something to be real.
So it's safe to say that this deep dive has left us with more questions than answers. But I think that's a good thing, right?
Absolutely. The best science often does that. It opens up new avenues of exploration, it pushes us to question our assumptions, and it reminds us just how much more there is to discover about the universe we live in.
It's like we've been handed this amazing puzzle box and we're just starting to figure out how to open it.
And who knows what wonders we'll find inside.
Well, on that note, a huge thank you to you for guiding us through this incredible journey into the heart of quantum weirdness.
It's been my pleasure.
And to all of you listening, thank you for joining us on this deep dive. We hope it's left you with a sense of wonder, a thirst for knowledge, and maybe even a touch of existential awe. Until next time, keep exploring, keep asking those big questions, and never stop being curious about the universe and all its mysteries. We'll see you in the great beyond of knowledge.
Ever get this feeling like
Like the universe is kind of messing with us. Like
Yeah.
it's got these secrets, right? And it's just waiting
oh yeah,
to like totally blow our mind.
absolutely.
Well, buckle up because today we're going deep on one of those secrets, quantum entanglement.
Ooh.
And thankfully,
We've got our expert here.
to help us unpack it all,
Yes.
we're diving into a paper.
That, let me tell you, shook up the physics world. John Bell, 1964.
Oh, this is a juicy one. We're talking about a clash of the titans here. Einstein
I love it.
versus quantum mechanics.
The drama.
Einstein, champion of,
Common sense.
common sense, right?
Yeah.
Up against quantum mechanics.
All this weirdness.
All the weirdness.
Where do we even start?
Well, at the heart of it is this idea called local realism.
Okay.
And this is something Einstein, he really, really believed in.
Okay.
It's this idea that objects, they have definite properties.
Even if we're not looking at them.
Right. So,
Like, an apple is an apple, whether or not
Yeah.
that's it.
exactly. So think of it like a coin toss.
Okay.
Heads or tails, it's got to be one or the other, right?
Right.
Even if we don't actually look at the result.
Got it.
Makes sense.
So quantum mechanics, it's like it throws the rule book out.
Throws it right out the window. It's like, hold on, that coin, it's both heads and tails until you actually look at it.
Okay. Now my mind is starting to bend a little bit.
Right. And Einstein, along with Podolsky and Rosen.
They're like, okay, let's put this to the test.
Oh.
They come up with this thought experiment.
All right.
And this is where we get the EPR paradox.
EPR, so.
Einstein-Podolsky-Rosen.
Right. Got it.
The names are all right there.
Catchy. So, what do these guys imagine?
Okay, so picture two particles.
They're linked, but not just any kind of linked.
Okay.
They're entangled.
Entangled. Right.
It means if you know the state of one.
You instantly know the state of the other, no matter how far apart they are. Wait, instantly. Like faster than the speed of light. Instantly.
You got it.
Now that sounds like something Einstein would have a problem with.
Oh, he did. He called it spooky action at a distance.
Spooky action, right. Like these particles have their own secret chat going on, breaking all the rules.
Exactly. He just couldn't square it with his whole local realism thing.
Right, of course. So this is where I'm guessing
John Bell
enters the scene.
steps in.
Doesn't come in with like some big philosophical argument.
No.
No, he's got a theorem, a mathematical tool.
Ooh.
He's like, let's put this entanglement idea to the test.
Love it.
So what's this Bell's theorem actually saying?
It says if there are these hidden variables.
Hidden variable.
Right, like things we can't see that are influencing these particles.
In a way that keeps things local and real, like Einstein wanted?
Then there's a limit to how correlated their behavior can be.
Okay, there's a limit. Go on.
But, and this is a big but, quantum mechanics.
It's saying the correlations, they go way beyond that limit.
So it's like quantum mechanics is saying, nope, we're even weirder than you thought.
Way weirder.
This is big. Are we talking about like breaking reality as we know it?
We might be. And Bell's theorem,
It was designed to expose that crack in the foundation.
it's local realism versus quantum mechanics. And the implications are, well,
Yeah.
huge.
Okay, so we're left hanging with this cliffhanger.
This face-off, Einstein and his local realism
Yeah.
versus quantum mechanics, right?
Yeah.
And Bell's theorem,
It's going to be the judge. What happens next?
well, the story gets even better, see?
Bell's theorem, it wasn't just some theoretical idea.
Okay.
It gave us a way to actually test entanglement in the lab.
Oh, wow. So we're not just in our heads anymore.
Nope, we're talking real-world experiments.
Wow.
And guess what?
They confirmed it. Entanglement is real.
No way. So the spooky connections, Einstein wasn't just being grumpy.
Yeah.
They're actually happening.
They're happening. It's like the universe read the script.
And decided to go with the weird ending.
I mean, it really is mind-blowing. It's like those particles.
To have the secret language, and we're
Mhm.
just starting to listen in.
Exactly. It's like we've been missing this whole other layer of reality.
This connection that goes beyond our usual ideas of space and time.
So does this mean Einstein was, like, totally wrong?
You know, it's not so much about being right or wrong.
Okay.
Einstein's skepticism, his questions, they were so important.
In what way?
Well, they pushed us to really dig deep.
To test these ideas, and that's how we make progress in science.
Right, so even if his ideas weren't spot on.
His way of thinking, that's what got us here.
Exactly. He challenged us.
And that led to some really groundbreaking discoveries.
It makes you wonder, are there other impossible things out there?
That might turn out to be true.
Oh, I'm sure of it. That's what's so exciting about this field.
We're just scratching the surface of what quantum mechanics can tell us about the universe.
Okay, I am officially mind blown.
Just wait. It gets even wilder.
So where do we go from here? We've got this universe that's even stranger than we thought, with particles potentially talking across the cosmos. What does it all mean?
That's the million-dollar question, isn't it? But that's the beauty of it, right? We're not afraid to ask these big, mind-bending questions.
Right. It's not like we have all the answers just because we've got Bell's theorem.
Exactly.
Right.
If anything, it's opened up even more questions, like how far does this entanglement thing go?
Yeah, and what else haven't we even thought to ask about the universe?
And that's what makes this whole area of research so exciting. It's like we've just started exploring a whole new continent of scientific discovery.
It's kind of humbling in a way to think how much we don't know.
Oh, absolutely. But it's also incredibly inspiring. It reminds us that there's always more to learn, more to discover, more to understand.
So to our listeners, keep that sense of wonder alive. The universe is full of surprises, and who knows what mind-blowing discoveries await us just around the corner.